Before heading to the video, if you haven't subscribed the channel, do subscribe it and don't forget to click the bell icon for the latest update notification. If you like the video, do like, comment and share. Stay tuned with LearnBay.co. Happy learning!
We have so far seen a few things in time series. First of all, what components does a time series have? Then, what are the different ways in which we can forecast using moving average and three methods of exponential smoothing. So, moving average is also a smoothing technique, and so that makes it four smoothing techniques in order to use that for forecasting purpose. So what we are going to do today is we'll try and see a little bit of time series modeling through Arima, and we will look at the end-to-end Python implementation of a problem with regards to five or six methodologies. Okay, so let's begin. Now, when we think of time series, the first thing that we should take note of is that these observations are recorded against time. All right. So therefore, what happens is that if you have a collection of random variables ordered in time, which is often denoted as yt or xt, then where then it is following something called a stochastic process. So when we think of a stochastic process, it has to be driven by time actually. Now, when we say that a time series is stationary, it means that as time progresses, the average value of the metric or what we are studying, average value doesn't change over time. Thanks, Pranav, for joining. Pranav, am I audible clearly to you?
Yeah.
Okay, perfect. So we just started, and I was just talking about what stationarity is all about. So stationarity, guys, essentially means that look, even if you have time moving from one end to the other as time progresses, the average value of the what do you call it, the y variable, the time series variable, is not really changing. What this means is, although the levels may have changed, but it adjusts itself plus my positive negative in such a way that it really changes, the average remains constant. So that is stationarity. A non-stationary time series is that the average value will depend on time. So what happens in case of properties is that when you look at the mean of a stationary time series, you will see that it is a constant, and that is why it is denoted as mu here. If you look at the variance of the time series, it again is in that calculation of the variance, the mean is a constant value because we saw earlier that the mean is constant. And similarly, in covariance calculation as well, the mean continues to be constant. So property of stationarity, all just remember that if you're asked with this question, or if you're trying to like conceptually understand, just think that the average value of the time series metric is not going to change as time changes or progresses. Okay, let's come to something which is called white noise. Okay, now white noise is a stationary stochastic process, but here the average value is exactly zero. So if you look at the graph here, you will see that the values themselves cancel each other out about the zero line, and the average value continues to be zero. So if it is a purely random or white noise situation, then we say that there is a constant variance. When we say there is a constant variance about the mean, and in this case, the mean is zero. But if you recall, there is something I mentioned in the first class of time series, very important. That is, in time series, the basic difference between time series and supervised learning problem is that in supervised learning problem, all the data points in your sample is assumed to be independent of each other, right? So if it is customer data or product data, the assumption is that one row of data is actually independent of what you have in the subsequent row. Okay, but if you look at white noise process, I'm sorry, if you look at time series, that is not the case. So today's value depends on yesterday's value. Yesterday's value depends on day before. and therefore the fundamental assumption of supervised learning gets violated in case of time series. That's a fundamental difference between time series and supervised learning. Now, and that should be the way to answer that question in case you're asked that question in interviews, guys, that why can't we simply use supervised techniques in case of time series, and you should answer that, it's fundamentally different. Now let's talk a little bit about why white noise is is sort of a slightly different time series. So white noise actually is a time series, no doubt about it, because if you look at the properties of time series, it satisfies all properties. It is measured against time. It is definitely stochastic because, like I said, it's measured against time, so it has to be stochastic. The only issue is that white noise is actually identically and independently distributed. So what that means is that if you satisfy this condition, if you satisfy this condition, then the the problem arises when you want to forecast anything. So if you want to forecast, the values must be dependent. Only then you can actually forecast using time, because in this case forecasting is actually not possible, because it's first of all it's completely independent distributed, and it's white noise. So if you see the line that has gone here, that is the line for the average value. So really there is no trend, nothing that you can decipher from this kind of movement of data. Okay, let's look at one non-stationary process. But by the way, white noise is actually a stationary process because mean is constant. So, but it is not useful for forecasting, but it is nevertheless a stationary example of a stationary process. An example of a non-stationary process is what we call as a drunkard's walk problem. So if a drunkard leaves a bar and moves a random distance ut at a time t, so and it continues to walk indefinitely, what will happen is it will eventually drift further and further away from the bar. So all you got to do is just remember that today's value of time, the current value is equal to the yesterday's value plus a random shock. So, like if this guy started his distance here and he moved here, he can go in any direction. That's not the problem here. The problem is that he goes away, depending on how much distance he has traveled. The next data point will be the distance traveled here plus a random shock. So the direction here that you see, right, the theta angle is the random shock. So it could have been in this way also, right? It could have been that way also. So it's randomly chosen which direction the person will go. That's why there's a random shock here. But eventually, if you see, it will move further and further away. So as time progresses, all these points are actually far away. Then if you look at all these points, even these points, they're actually far away from the starting point. So um, so the problem here is that the average distance traveled from the bar increases as time progresses, right? So it is a non-stationary process because the average value is shifting with time. So we have a few things to check stationarity and non-stationarity. One thing is what we call as a autocorrelation function. So if you look at the the autocorrelation function, what it really means is that if you take two values of time series, right, and they are correlated to each other, then only then we can create a autocorrelation function. And over here we are basically calculating the covariance between yt, which is the current value of the time series, and then k periods ahead, yt plus k, and divided by the standard deviations of the similar period. So we will see this in Python, how it's created, and it will become much more real to understand. For different time series, the correlogram tapers off quickly. There's non-stationary time, it rises gradually. So this is the important point to keep in mind. So when you build a correlogram, you will see that the graph actually looks like somewhat like this. Okay. Now, if it is a if it dies off, like it converges very quickly, right? Then we say it is called stationary. Otherwise, we call it non-stationary. So if it's a there are examples that you will see later on. So instead of me scribbling, but you'll see it. So what happens is that we look at how it's dying off. So that's one way to determine. The other way, of course, is to actually perform the Dickey-Fuller test. Okay. So the Dickey-Fuller test is estimated in three different forms. It's assumed that the error term is uncorrelated. So under the null hypothesis, so this is important. So under the null hypothesis, if you recall, we had studied hypothesis testing in stats. So we say that there is no um, autocorrelation actually. I mean, the UT is the, I mean, there is no correlation in error, or in other words, autocorrelation. Yeah, alternate hypothesis, of course, is the opposite of, yeah, there is correlation. So greater is greater than zero correlation. So we're saying that there are four ways, right? So either we take a random walk. So over here, look at the definition of random walk here. It's basically saying the distance traveled, the change in distance traveled is equal to a fraction of what you had done last time plus a random shock, a random walk with drift. So a fraction of what you did last time plus some sort of a random shock here plus a drift, a constant drift. So it says that if I had covered x distance in the last move, this move I will be covering a factor x multiplied by a factor plus some randomness will be there, or on top of this there will be some sort of constant move, a constant drift. Constantly I'm going to go away further and further away from the origin. And if there is a time dependent drift, we call it a stochastic trend, that with time my drift also is changing, then it becomes a stochastic trend. So these are four forms in which you can do Dickey-Fuller test. So suppose yt can be described by the following equation. So you have a drift, and then you have a stochastic trend. You've got this movement based on the last period and also a random shock there. Okay. Now what's happening here is that you're basically using OLS to run an unrestricted regression. So you're saying, okay, yt minus 1. So if you do that on both sides, you'll see alpha plus beta t plus rho minus 1. And when you actually kind of cancel it out, you will find that the sum of squares of residuals in the restricted and unrestricted regressions are used to calculate the AF statistic. And then finally, you will be able to create that critical value. So this is very theoretical. Unless we go to Python, may not be that clear. I just want to touch upon the element of what we do in order to make the data stationary, and then move to the code so that you guys can follow the code, and we'll take a problem and then we'll try to solve it end to end. Okay. Okay. So now we start time series modeling. So till now, what all we have discussed? We discussed what is stationarity. Okay. We discussed the Dickey-Fuller test for testing of stationarity. And we also discussed the ACF function. We know that if it is tapering off quickly, then it is called stationary, or slowly, then it is called non-stationary. This is what we've covered so far. So now, time series modeling, I'm also forecasting a variable yielding only its past values. Now, the best variables unrelated to other variables is in a structural model. And an auto-regressive process is basically this, that, in the future value, this is where the future value is nothing but a function of your past time series values. That is how we define an auto-regressive model or an auto-regressive process. So if we're saying it's regressing on the past values. So yt will regress on yt minus 1, yt minus 2, etc. And it's sort of automatic in a time series. So we express it that way. Now there are right? So in order to build a time series model, what are the steps that we'll follow? So first thing to do is to have a graph the data series to see what patterns are present in the data and decompose. So this is step one. Test the data for stationarity with decoupler test. That's two. Then if original time series is not stationary, then difference it until it is actually. The number of differences p to make the data stationary is determined using decoupler test, or uh, you can sometimes uh, you can sort of do trial and error also, no problem. Typically one or two differences is what we'll see that in the later on. Use the stationary or difference series actually to determine the number of lags that are present before the forecast on the historical period. Now uh, you can so then the number of lags become the other parameter of the auto regression process. And what we are saying is that we had the original series, right? Now we have a difference series. So this is where my q will come from. And when I move from original series to the difference series, how many times I actually made a difference is where my p comes from. Assume what are the assumptions, right? So assume series you're focusing is really random, so there is no trend, seasonal, cyclical pattern. Series is stationary or white noise. To guarantee this assumption, we must make the data stationary. Definitely assume that the variability is constant. So in other words, it's the same for future as well as it is for the past. Basically we are saying that variability about the mean, that needs to be constant. So this variability is what I'm talking about. This needs to be constant, and the direction can change. Of course, you can have it like this, no problem, like that. You know, over a period of time, it can go on, but this gap continues to be the same. So it's a variation. It can. This is a crucial assumption because it we can actually test the constant variance by testing correlation over time. Because if the variance changes over time, then the forecast will explode. So what will happen is, imagine that you have a time series where this is to be the variation, and now it again changes. So can you see this variation increasing over time? Guys, can you see that? So who knows that after say 50 years or whatever number of period you want to forecast, the variation is going to be so big that it is uncontrollable. So that way, the data has to be, we have a term for it. This called homostochastic. Okay, so let's come to the interesting part. Like, how do we make the data stationary? If stationarity is important, then how do we go about it? Right? So what we do is we simply calculate the value, the given value, and we subtract the older value from it. And it's called the first difference. The first difference expressed as d1t is nothing but yt minus yt minus 1. It's important because sometimes we achieve stationarity in the first difference itself, and that way the data is not too modified. But if you look at the second difference, I mean, it's again the same thing. Present value minus the older value. Only this time the second difference process is applied on the differenced time series and not the original time series. So you're saying that d2t is equal to d1t minus d1t minus 1, and so on. So the third difference is again going to be made on the second difference column, and so on. Where do we stop? We stop when the data, when it becomes stationary. That's when we stop. Let's have a look at the example here. It's a picture here, but it should drive home the point that, let's look at this data. This is the time series data, right? So now we've got D, which is C10 minus C9, nothing but this value minus this value. So it comes out as 0.41, which is this, and it goes on. So obviously this is a truncated data. Therefore we have this value, otherwise we won't have this value. This will not be there. Yeah, if there's obviously data points below this, that's why you have this. Otherwise, it will be blank. D2T is again minus 1.41 minus 0.41, so it's minus 1.82, which is here, and so on. So D1T in period one is 0.41. D1T in period 2 is minus 0.41. D2T in period 1 is this. D2T in period 2 is 1.66. Okay, so that is how we difference the data. Now what we do is, first we do decay fuller test. Is the original time series stationary? If not, that's fine. So in order to do this by hand, we first have to regress the time series on the difference data. Now calculate the T ratio for the beta value. Now you don't have to do this. You don't have to do this because all softwares do it. I don't know if you guys remember, but in case of simple linear regression, um, yeah, right? So if this is a simple linear regression equation, B and C, these are regression coefficients. And B and C follow small t distribution. So that's why we call it, T ratio. Then DF test statistic is T statistic. It's more negative. So the rest is just hypothesis testing. You can go through it, but you will see it in the example. Similarly, we do the next level of stationarity for the second level testing. So it's nothing new here, except what we have it in the earlier slide. So similarly, in third testing also. Now, if a stationary series is actually stationary, how does decay fuller test is work? It's working for us. If it is stationary, then it oscillates about the mean and has a slope 0. If it is actually stationary, if one period lag yt minus 1 is used to predict yt, then they turn out to be good predictors of each other because they have the same mean, and t statistic on B will be significant for the first difference as the dependent variable and the second difference as the independent variable. Lagging in the data 1 causes the two series to be inversely related, so the slope is negative. So this, basically what is happening here is that if you lag the data, then the relationship just flips over, and that's why you have the slope to be negative. So in the earlier example, we discussed that DF statistic of 3 is more negative than 2.9. So that's why the original series is stationary and differencing is not necessary. So if it comes out as significant, then you're fine. If the DF statistic is significant, then the original series is not, it doesn't need to be stationarized. So you can see here that this is the original series, the black line, that's the given data. Then the red line here is the plot of the first difference, right? Now, what you're doing is you're actually fitting a linear regression line over here, and then you're trying to compare. So you're obtaining the beta. Beta is nothing but the regression coefficient, and then you have the ratio here. The t statistic is minus 1.8. Okay, so we saw that. So that's the t statistic here. So it is basically stationary. No, then 1 second. The probability value is given as 0.063, so which is actually significant. So it should be fine. The data is, but it looks like it's, hang on, so just a second. So yeah, okay. So here's the deal, right? So because of this problem, that the data will always have a certain value independent of the difference of series. So that's why the mean is not constant. But if you purely look at the decay fuller, the regression test here, it looks like it's actually coming out to be significant. So the data can be further stationarized. So let's see. Now what you do is you take the second difference, and the second difference is plotted in the blue line. So you can see the second difference starts to look more like a white noise. Okay. Now, so because there is no trend in either series, intercept of 0.1 to 1 or about near about 0. So the mean is likely to be constant. So over here, the probability value became even smaller than what it was over here. So that's why this series is actually now stationary, but we are stationarizing it with D2T and not D1T. So we did not, stop at D1T. We had to move to D2T. Okay. So as a thumb rule, we keep on checking, but just don't go beyond 6 differences. So it should be okay. Select the number of differences with a DR test statistic more than minus 2.9. So how did we come at 2.9? So 2.9 is where I think this is the 5%. Yeah, so the 5% level of significance is 2.9. Anything less than 2.9 makes it you know anything less than 2.9 makes it significant. So if there is a difference, if there is a number of differences that help you achieve values lower than 2.9 minus 2.9, then that makes it statistically significant. Okay. So now there is the other problem of determining the number of lags. So once we have determined the number of differences, we know what form or the auto regression model is going to be fitting. Number of differences, comma, number of lags, right? So if the series is stationary with one difference, then it's just one, right? And then the only thing remaining for us to solve is the Q part, which is going to be the number of lags. So let's do that. So the actual process to do this is fairly lengthy. Okay. Now we say that partial correlation coefficients are actually used to estimate the number of lags. So if this series D1T is stationary, then in order to test for one lag, what we do, we use B1 from the regression model. If you're testing for two lags, then we basically just take a B2 from the regression model, the second difference value. I mean, in the first difference series, the second lag. The third, if you want to test for three lags, then we have to lag it by 3 and then take the regression coefficient there. So after each regression, we only use the beta for the maximum number of lags. That is the bold ones above, right? So these are the bold ones. And then we use the T statistic to determine the contribution of the last lag, basically to explaining D1T. So this is quite similar to your multiple regression concepts. Okay, now when the whole problem is that of explaining the variance in Y, right? So therefore, when you look at each of these regression coefficients, what you want to do is you want to estimate the impact this regression coefficient actually has on the Y. So that's what we are trying to say. That's all we're saying. That if you look at the T statistic on the regression coefficients, we determine what is the contribution of the last lag. What is the contribution of this lag? This is the last lag here. In this case, it is D1, T1 minus 3, right? So what is the contribution of this into the overall series? So that's what we're saying. So this means that there's a lot of regression coefficient that you have to perform, right? So thankfully, Python does that quickly. Most every software will do that quickly wherever you can build a time series model on. But let's have a look at a few visuals in order to figure out what we were talking about earlier. So if you see this one, right? So this one is actually very quickly. If you see, the tapering off happened very quickly, right? So this is how the tapering off happened. So this looks like a stationary series output. This one, the tapering off happens, but it happens very, very in a dampened fashion. This one is a quick one. This is extremely slowly. So this is very, very slow. You have to go all the way down. But this slope is quite steep. and this one is in an exponential fashion. It's reducing, but there is no oscillation. So what you have to do is just keep these 2 points in mind. Okay, that if you have it cuts off or dies down rapidly, then the series is stationary. If it dies down slowly or very slowly, then the series is non-stationary. So just keep this in mind. It should be okay. So that brings us to a quick end to our problem on time series theory, right? So let's move to the Python code. So what we're going to do is, yep. So we'll take up a problem. We took up a similar problem earlier, but this is a pretty popular problem of air passengers. Now I want to also show you one more thing that you can do with regards to, I don't know if you guys got a chance to see the data. There is a, okay, I think I haven't shared the data yet. So it's called the jet rail problem. I will share that also here somewhere. Oops. Oh my God, no. 1 second, this is code for me. How many of you are actually paying attention and how many of you are actually working? Anybody has any questions so far? Guys, do I have your attention? Okay. Maybe you guys are multitasking between work and project, right? Okay, thank you. Okay, thanks. Guys, please stop me whenever you want to and have a discussion on any questions you may have. So we start, what we do is we're looking at the airline passenger data, and what we will try to do is, if you just go through the browse through the code, so we have this data set. We're going to first plot the original time series. Then we will try to decompose the time series into different parts to see what kind of, if you take the additive model or if you take the, the multiplicative model, do we see any sort of decomposition? Then I will divide the time frame into 2 parts, one for training and the other one I'll use for testing. I'll keep the maximum available data for training and then the rest for validation. Then we will come to, yeah. So this is basically every methodology. So I've built this code in such a way that, it's very step by step. So we'll start with a 9 forecast. I'll explain in a bit what 9 forecast is. Then we go to average forecast. Okay. We basically use the averages to forecast. And then at every stage, we will calculate the RMSE value. So if you just pay attention to the RMSE value, you can see it's 102. Then if you go to average, it goes to 226. This is pretty bad, right? It is increasing. And then at the end of the code, you will see that we ended up with 18 with seasonal ARIMA. So it will tell you how we can approach a problem step by step. And also when you construct your own time series models or projects, right, wherever you're working, or if it's a new project you're working on, it's better to show that you have tried a range of things and then you have narrowed down on a certain thing because it makes sense from an accuracy point of view. Okay, so we'll take a step-by-step approach. So we go ahead and I'm going to run the code right now. So I'm just going to import the usual libraries. It's done. Then I'm going to go ahead and import the data. So over here, remember that, it's important that the index actually is made the month or the time component of the data time variable is going to be the index. That's how we will have to slice the data later on. So we have to mention that what is the index column. So in this case, we'll have to mention the index column separately, because we need to make sure that month is the index column in this case. Okay, and parse dates equal to true. So we will have to clearly call out that under the index, the value that the data that is present is in the form of dates. So let's just make sure that we parse that. So once we do that, we take a quick first 5 observations to see how it looks like. So we can see that it contains a column called month, and then it contains a all the passengers corresponding to it. These are the airline passengers. So I at this stage want to make sure that what exactly is my index really a date time index or not, right? So I just go ahead and I just basically do a df.index, and over here I know that it is following the date time 64 ns. So this is the this is the thing that this is basically the format of the date time index, and the data type should be date time 64 ns in order to make sure that it is indeed a date time index in your time series data, and your indexing has happened in the right column. Okay, can you give me a moment? I'll just drink a glass of water and come. Just one moment. Okay. All right. Now that the data frame is ready and the data is ingested properly, let's have a look at what it looks like. So I'm plotting it. So we can see that a few things we can straight away see. It appears that there is some sort of movement with time, and we can call that as trend. So there is a certain increase that we can see with regards to trend, and it looks like there is some seasonal impact as well, just that we don't know what is a definite range to take for a season. So whether it's a season per quarter or a season per other movements, but we can see that there are minor fluctuations here also. So it's an interesting data problem to work on. What I want to do next is basically break this down and decompose the time series into its original components. So can any one of you tell me what are the components of a time series? Anyone in the chat window can write. What are the different components of a time series? So there are 4 components of a time series. First is called trend. Second is seasonal. Third is called cyclical. And the fourth one is irregular or random component. Okay. Now, when we move to the decomposition part, so over here from stat_model.tsa seasonal, we import seasonal decompose, and we are basically passing the data frame, and over in the data frame we're calling out the particular column that has to be decomposed, and then the form of the model, right? And we are plotting it. We're plotting both the cases here, and we're saying the first one, because we're choosing the multiplicative model of the time series, we are basically calling it to be multiplicative decompose, and the second one is an additive decompose, so we have chosen to call it like that, right? So let's just run it. So you'll see that I'm not sure what's going on. Just a moment. Yeah. So this is the observed time series, both cases. This is the trend line. It, because of the scale, it looks like the same. So the trend line is there. It has been able to decompose. In such a way that seasonal and residual are taken out. So seasonal component, as you can see, there is a definite fluctuations happening, and so is the case within. I mean, if you look at multiplicative versus additive, in both cases, you'll find the fluctuations to be present. It pretty much looks the same. This looks like the same two graph, but do you know where the difference is coming, or you should be noticing, is how the residuals look like. Look at the residual graph. Are they the same? They're not the same. Why are they not the same? Because within a multiplicative decomposition framework, the trend estimation or the seasonal component or seasonal index estimation is not exactly the same as what we have in additive. So if you look at the range here, -50 to 50, in case of additive, in case of multiplicative is 0.8 to you know 0.8 to 1.2. So the trend actually is the same. Agreed that the trend is same, but the seasonal component and therefore the residuals are totally different because of the structure of the time series. So we've taken two assumptions. One, in case that let's fit a additive structure to see how it looks like, and in case of multiplicative, how it looks like. Okay, so now we want to understand how much is the data given to me. So I'm just ran a quick shape here to see 144 observations given to me. What I want to do is I want to basically take all the rows up to the last 12 rows actually. So if all my 144, right, so the data is given to me in terms of months, right? So I would say, let me just use one second. Yeah. So I will use everything up to the, just set 1 year away for testing 12 data points, and until the -12th point from the end of the data frame, we are fine to use all of these points as training, and we just leave 1 year out for testing purposes. So how much, if you run this, like how much do you get as data for training? So if you do that, you find 132. In shape also you find 12. Okay, now if I want to plot it, so I just wanted to quickly see that what is going on in the training data. So it looks like I have captured, I have a fair amount of trends, etc., seasonality to capture. So if I'm able to fit a model onto this one, it will probably do a good job of learning from the data. And then within the testing, I have just 1 year, which is 1960. So all my points are plotted for that one particular year, and therefore if you just plot the test data, you get the plot only for that year. Okay, till this part it should be fine. So we will come to this both of these a little bit later. Sorry, the chat. Do we have to separate date, year and day, or it will do the job automatically? No. So iLock is what will separate the data. The forecasting will happen against the given time component. In this case, that is months. So Pranab, we don't have data at a daily level, or we don't have data at a yearly level. We only have it at sorry, let's just take a look. Yeah. Yes. So I think you should be able to hear me now. The idea is that, the data, whatever level you have, that at that level, the forecasting is going to take place. Okay. So let's come to the autocorrelation and partial autocorrelation little bit later in the code. So we start with what we call as naive method of forecasting. Okay. So over here, this is a markdown. Yeah. So if you look at it, we just okay. Let me just explain what naive method is. The naive method is nothing but it assumes that the next period forecast is equal to the last data point, just the very last data point. Okay. And it continues like that. That is the only data point that it will continue on. So whatever is given as the last point, all the future is going to look exactly like that. That is what the naive method does. So what we are doing here is we are converting, basically we are converting the data into a NumPy array, and then we are using we are actually copying, creating a copy of the test data so that the original test data does not get impacted. And in the test data itself, which is now a copy, y hat is a copy. So I'm creating a column called naive. And what this does is, this is basically in that array itself, I take the value of the array and I basically say that, okay, take the entire length, go to the last point and go to the last -1. So that brings me to this particular point. Look at my cursor. So it brings me to this point here at this stage. Okay, now if I'm plotting the y hat, if I'm plotting the y hat index on the x-axis, of course, right? This is the and the y hat value. So the y hat naive, which is nothing but the naive forecast, and labeling it as naive forecast. This is the green line. So you can see that the green line is actually not close to the yellow line. The green line is very far off. It is doing a very poor job actually. So in order to assess how poor a job it is doing, I am importing metrics from sklearn, and from math I'm taking sqrt function. So sqrt will allow me to calculate the RMSE. Now RMSE stands for root mean squared error. Over here, the way to do that is we take the square root of matrix dot mean squared error. I'm taking mean squared error as a directly from the matrix library, and within the mean square error function, I'm passing two things. I'm saying test dot passengers, which is nothing but the actuals, comma forecast. Always do that. So you have actuals, comma forecast passed within the mean squared error function, and we then calculate the RMSE value. In the next step, we're just printing it. So we're saying RMSE for naive method is 102.97. So it is fairly high RMSE for us to even begin. I mean, if you don't want to, if you cannot make sense of the number, I mean, say like you might just ask, okay, how would I know if the number is big enough? I mean, if it is 100 versus 200 versus 300, so what is going to be the deal? That's why we don't look at only the number, but we also look at the the closeness of value. So the green line is actually quite close, not that close to the orange line. Second thing is forecasting using the average method. Over here, what's happening is we're saying that we are copying, of course, y hat copy. We're saying that y hat average is a it's a copy. So create a column via average forecast, and we take the average value of the training data and put that in this particular forecast in the testing data. Okay, and then the rest of it is very simple, in which we are looking at the passengers and essentially plotting it. So let's look at how, where do we end up. So the average is somewhere here, and that's what it is plotting. And the RMSE value would have really shot up. So it has, as expected, it has shot up. So this doesn't take much long to perform. The RMSE value has shot up. So this is very, like, absolutely, like, doesn't make sense at all. So let's see if we want to use moving average. Okay. Yeah. So again, we have a copy made of the test data. Over here, we're saying, let's create a column called moving average forecast. And we basically take the 5-period moving average. Okay. We take the 5-period moving average. We take the, the um, average, moving average actually, and then ILOC -1. So we take the last value of that, and then we basically use that to forecast for the rest of this. So the last value calculated using the moving average, that becomes the forecast for the rest of the period. So at least what has happened between the general average and moving average is that this average value has at least come within the yellow line. Okay. So as you can see, because of the green line being close to the yellow line, the RMSE value has improved. It is now 83. So where were we earlier? We were 226. Now we came down to 83. So far, there are 3 things we looked at. One is a knife method, does not help us much. Give me one moment, guys. Okay. Right. So knife method we saw, then we saw the average, then we saw the moving average. We can so far see that the moving average is the best of the lot in the 3 methods that we see. Now let's move to the next things in terms of smoothing techniques, in terms of the exponential smoothing. Okay. So what we're going to do here is that we will try 3 kinds of exponential smoothing: simple, holds linear trend, and hold winter. So I'm quickly going to tell you what each of these are. You've gone through the theory. Later on, you can watch the video also. So the simple exponential smoothing assumes that there is no trend or there is no seasonality. Without those assumptions, it will try to predict. It will try to fit into the data, and then you will calculate the the forecast. Okay. Now, so the forecast we are going to make is basically on the test data. In other words, the next 12 period forecast. So the test data is the last 1 year kept aside, right? So 12 data points. So forecast that we will make with any of these processes is going to be the next 12 points. So let's start with simple exponential smoothing. And in the next, and as we progress in the next one, I'll tell you what the theory is. So in case of simple exponential, what we do is we take statmodel.tsi.api. From there, we include 3 things: exponential smoothing, simple exponential, and hold. So first we make a copy of the test data, and then we basically fit the simple exponential smoothing using a array of the given series within the data frame, and the passengers, the series passenger series is converted into an array, and then we're saying dot fit smoothing level 0.8 optimized false. While I cannot recall what optimized is, you may want to look that up in the documentation, but smoothing level 0.8 is the alpha that we spoke about. Okay. Now, in order to figure out what is the best smoothing level, what you can do is run this, of course. Let's just run this. We can see that the green line is here. How much RMSE did it bring to us? Let's have a look. We have called this as SES, right? So we'll use that column for calculating RMSE. 107. So interestingly, moving average was 83. This is now 107. Can I make changes to this and make it better? So let's have a look at it if it is possible. Well, it's inside. Let me have a look at the RMSE value. Slight improvement. 107 becomes 96. Still does not beat the moving average. So you can change it further. So let's say we change it further and bring it to a much lower number. We can see that it is now begun to suffer a lot because it goes up to 38. It doesn't really make any sense going that way down. But what about 0.2? We can at least try that part out, or maybe 0.15 between 0.1 and 0.2. It's a little iterative, but try it out to see. Yeah, okay. 0.15 you have reduced to 90. Good. So if that's the case, then maybe 2 will be better. If 2.5 is actually, let's just try that out. Yeah, you see 2.5 is still 90. So it does not look like it's improving any further. In order to be sure, let's do 0.4. Ideally, it should start to look worse. .97. So you can see it was good till 0.1415, and then it starts to shoot up. Okay, so we're at 97 RMSE. Okay, all right. So let's see if you want to you want to assume that there is a trend. Now in simple exponential smoothing, we don't assume any sort of trend or exponential any sort of seasonality in the data. But in case of Holt's exponential smoothing, the trend is assumed. It's already factored in. The only question is, will it make matters easy or will it make matters worse? Okay, let's have a look. So we basically keep the smoothing constant 0.3, and then we forecast for the entire length of test data, and then we plot it out. But in order to make sure that we are doing the whole exponential smoothing and not simple, just look at the difference in the code. We were fitting simple EXP smoothing. Now we are fitting Holt over here. Holt. Can you see that? Okay, let's quickly run this. Okay, now interestingly, you will start to see some change. So this green line was a flat line parallel to x-axis. That means there was no angular relationship or no trend relationship in this forecast, and that is absolutely fine. It makes sense because simple exponential smoothing, assumes that there is no trend in the data. So there is there is no slope is what it's assuming. But in case of Holt, you will see that there is line has become tilted. The line has become tilted. And this is the biggest difference between Holt and simple exponential smoothing. Holt assumes trend. Interestingly, the RMSE value now reduces from 97 to 80. So we are actually making progress in a step-by-step way. So I'm not sure I follow the question.
There will be 3 smoothing constants for holds.
Yeah, no. 2. Smoothing constant 3 will be here. In case of Holt winter, you will have. In case of Holt winter, you
3.
have, seasonality will also come. Yeah, the rest is fine. So the rest is 2. So you can see this, right? 2. Smoothing level 0.3 and smoothing slope is the beta. So you might, we can try and improve on the slope. Let's just try and do 0.2. Yeah. So see, it actually becomes the opposite side. It doesn't really help. So we should all start with 0.1 and then move on from there. Yep, it actually improved a lot more than what it was earlier. So smoothing constant, if I keep as 0.1 and slope as 0.1, then my RMSE comes down to 75. So that's a big improvement from 97 to 75. So we'll try to see if what can we achieve by Holt winter actually. Okay. 1 second. Trying to clear this output. I think I probably may have removed the code entirely. Okay, this, I don't want to rewrite the code again, but I can probably import the code back in Jupyter. Okay. Upload it. Give me a moment, guys. Can I upload it somewhere? Yeah. Okay, we'll open up from here. My bad. Yeah. Okay. So yeah, where were we? We were at here, 75. Let's run the whole winter code again. Okay. Now, very interesting. The data in the test period is fitting, the forecasting in the test period is fitting the test data really well, right? We can see that. Now, what have I assumed? Seasonal period equal to 12. Every month is a season. What if I say that there are 4 seasons, meaning that every quarter is a season? Will it improve even further or will it not? Looks like it does not. So there's definitely more number of seasons for sure. So can I say every 2 months is a season, and so there are 6 seasons? It starts to look a little better because it actually starts to show that fluctuation. So it should be a spike here, as we know that there is a spike in the test data in reality. So then the other option only left for me is 12, because seasonality has to be in multiples, right? So this is where it perfectly fits. And when I do a RMSE, I get 22.71. Okay. So this is interesting. So this is where we are with regards to Holt winter. Now we have explored forecasting, smoothing methods, and therefore forecasting. We haven't really done any sort of modeling bit as of yet. So this is where we're going to now do. So we'll start by running a Eddy Fuller test. Same thing as slight modification of Dickey Fuller test. So what we're saying is that let's import Eddy Fuller function, and we will run it on passengers column on the in our data frame. So let's have a look. What seems to be the issue here? Okay. Yeah, it's stored in different columns. Yeah. So this test statistic is coming out to be like this, and definitely p-value is 0.99. Now, if you look at the p-value, this tells you that it is not significant. It means the data is actually not stationary. So it needs to be stationarized first. So this tells me that there has to be some sort of differencing activity done on the data. So before we now progress to ARIMA, we will try to difference the data, and the code for that was so we can actually make use of this section of the code. Should be okay. So again, guys, whatever comes out of the differencing process, right? Take it as directional, but you should. I firmly believe that you should iterate yourself on the data in order to make sure that you're able to identify the best set of parameters for your model. Okay, so I'm going to run this. Yeah, I think the zoom might be. So this is my original series. Okay, this is how my first difference looks like. This is how my second difference looks like. So the more and more the data starts to look like white noise, if you recall, this is what we discussed here, and we also saw it here, that more and more the data starts to look like white noise, the better it is, and we become more and more sure about the stationarity of the data. So the first difference, how do we get it? All we do is we say that plot the data frame, of course, dot diff. So that way, that's all you have to do in order to make the, calculate the first differencing and then plot it. So directly you can see that first difference has definitely improved the non-stationarity and brought it closer to stationarity, but second differencing really has made sure I think the data is stationary in this case. The other thing I'm doing is I'm plotting the ACF, or the the autocorrelation function. So why I'm doing this? Because the differencing tells me the different lags that I have to apply, because ARIMA has P, D, and Q. So you need to assess the P part. So that's what you try to do from the autocorrelation function. So over here you can see that this this doesn't die down that quick. I mean, it reaches negative very soon, and then it goes up again. But the overall convergence is actually very sharp in case of the first difference. In case of second difference, the sharpness increases even further. So in the first attempt itself, let's say by second order itself, it goes to the negative zone. And the blue line that you find is basically the critical zone. So beyond the critical zone is what we are interested in. So we can see that order 2 is where it is sticking out of critical zone. So we can safely say that it reaches stationarity in the second order of the differencing. And we saw this in the last comment here, that if it dies down quickly, rapidly, then it is an indicator that the series is stationary. Okay, so now let's import ARIMA, and once we do that, we then pass on the PDQ parameters of ARIMA, the order of ARIMA, and then fit the model and do a summary. So this should tell me which parameters are actually coming out to be significant. Okay, so now let's take the second order. Last two values of the time series is getting taken, one difference is getting taken, and moving average in so we're taking MAL1, MAL2. So that's why you have two. If you put 3 here, you'll probably see. So let's take arbitrary something, and otherwise, so 2, 2, 3, something like this. Let's see what we get. Some sort of an error. Yeah, the algorithm itself did not converge. So it ran into some issues by itself. 211 or maybe 111. Yeah, looks like this is also statistically it's fine, because all these coefficients are statistically significant. So from a purely statistical perspective, it does not look like a bad situation. Now, when we plot the residuals, it should follow white noise, and that's what we are trying to do here. We're saying model dot, we are basically taking the fitted model here and creating a data frame of residuals and plotting it over here, and also the density, just to see if the density is following a normal distribution and the residuals are following white noise or not. It is the case, but there is sufficient gap here, and this graph is also quite peaked. So we can try to calculate the RMSE value or we can do a visual. So we can see that there is some gap here typically, and that's something we can bridge. So we saw that the order is 2, the differencing is actually 2, and if we take 2 to 2, then what happens? Okay, so 2 is probably not going to work because it's not even significant. L1 is not significant, so that is an issue. So 2 is not going to work. So let's make it 1, 1, 2, and then let's see. Okay, so this is fine. This looks like it's fine because all these are statistically significant. The graph should appear more dense. It starts to look more dense. And now the blue line should come closer to the yellow line. It does to an extent. Can't be said that it doesn't. So it does to an extent. Now the interesting part is that we have taken 2, 1, 1, right? Oh, no, we haven't. Why was I getting a better result in 2, 1, 1? Yes, because it's all of them are 0. And then, okay, perfect. Right. Now, if you notice the exponential smoothing results, right, you will see that Holt Winter was doing much better because it has assumed seasonality as well. So in case of ARIMA, there's a seasonal variation of ARIMA called SAS ARIMA or SARIMA. So what we do here is we basically pass on the order, and then we pass on a seasonal order into the Sarimax function. So once we do that, we are basically able to make sure that ARIMA algorithm accounts for seasonality and then does the model fitting. Let's have a look at what it does. Okay, now let's quickly take a look at the coefficients and its level of significances. This is not exactly significant. So in case of seasonality, 2, 1, 1, 12. So let's change the order to what we used in ARIMA. That is 2, 1, 1 and not 1, 1, 2. 2, 1, 1. Non-stationary starting already is a primary is found with info stationary. Oh, okay. So it is running into that kind of challenge. Okay, 2, 1, 2 is what I have noted down my parameters for last time. Optimally, it is coming out to be 2, 1, 2. Let's just give it a minute. Okay, so this one is not in, is actually higher than 0.5. So that is not significant from that perspective. But let's look at the way it is forecasting. Yeah, it's not doing a bad job there. It's forecasting pretty well. If I take the yeah, that's what. So if I take the RMSE, you can see it drops all the way down to 14, which is pretty cool. 14.91. So you can see that currently that is the lowest RMSE that we've been able to achieve basis all the forecasting models step by step. Although there were a few iterations done at the end, it's not, and this is why I keep saying that data science is not going to be a situation where you are always able to, you're always in control about the outcome. The outcome sometimes is not going to be as per expectation, and you have to be patient enough to do the iterations yourself. You should, and I keep saying this in other forums as well, that you have to sort of be ready to fail. You're trying to test yourself out, and if the result is not coming, be ready to go back to the drawing board and get started all over again. So that's what I did with this particular code. When I was setting it up, there were numerous times when I did not actually get what I was looking for, but I was looking to set up a code which gives you a sense of a step-by-step approach, and how the root mean square value started to reduce as algorithms became more and more complex and more sophisticated, all the way leading up to the seasonal edema. And as you can see, we started with something in 200s, and now we have gone down to 14.91. So you should now be able to, you should now be able to use this code in order to solve at least a few problems on time series hands-on, and it should be good for you. So UCI repository has multiple time series data sets. It's a good place to practice things. So you can click on all data sets, and you click on time series, you can see 112 time series data sets. So a lot of time series data sets. Some of them are like really, big ones actually. So you can say appliances, energy prediction, air quality. You can probably do this. Data says 10 minutes for about 4.5 months. So you can go through these problems later on, but I just wanted to show you that this is also a repository where you can go and pick up data for practice purposes. Okay, guys, so that brings us to the end of time series.